next we're working on the Lab 5 hardware, which is the differential amplifier. The first step of this hardware is to measure VGS when there's 0 volts on the inputs. So ground both inputs of the amplifier, measure the bias current, and on the reference side make sure it's 4 milliamps, and measure VGSQ. So if we go over to our hardware, I've already constructed the circuit here, and I know it's a little bit of a mess, but try to follow along if you can. The top chip here contains the simple current source from Lab 4. So gates are connected together, sources are connected together. I have a 1.8K reference resistor, and you could measure the voltage across that resistor and do Ohm's law to figure out what the reference current is, same as we did for Lab 4. And the output here is the yellow wire that's going to go up to the sources of the diff pair, which are also connected by a brown wire here. If you can see, that connects the sources, and the gates. The gate on the right side is connected to ground through this black wire, and currently it's connected to the gate on the left side through this yellow wire. So both gates are grounded, and when we get to the next part I will move this connection basically. You don't have to change anything else to figure out the differential gain. The drains are connected with these green wires to the drains of the PMOS underneath, and the PMOS has gate drain connection here, and the gates are connected together through the top white wire, and the sources are connected together to the bottom white wire, and the sources are connected to the positive supply. And don't forget to hook up the body terminals of the NMOS and the PMOS, as I've shown for both chips. Okay, so I've tried to make it as nice as I could, but I know it's not easy to see. Okay, so if I go over to waveforms, let me open that up. I've set up plus and minus 5 volt supply here, and I'm currently measuring VGS of the input pair. So I have the orange wires for the voltmeter connected to the gate and the source of M1 or M2, and I'm getting 2.392 volts. So if I go over to Lab 5 and we want to measure VGS, which I just measured, and I out you can get if you connect a 1K resistor to the output to VDD, basically just measuring the output current in the same way we did for Lab 4. So you want to get a picture of your hardware now to include there, and we need a picture of differential gain and common mode gain. So let's go back to our hardware setup, and we need to reconfigure for differential gain. So I'm going to disconnect this ground connection to the left gate, and I'm going to drive this with the W1 input, or output I guess, of the analog discovery module. That's all I have to change to do the differential gain. I will move the scope probes though, because I want to look at the input signal, which is on the other side. It's the gate of the NMOS. And that's going to be measured to ground, so ground is on the other side. So it's the differential signal across the amplifier, the inputs. And we need another scope probe for the output. So blue is channel 2, blue wires, so I'm going to connect those. And this is the negative one, so that's going to also go to the gate. And the other blue wire is going to go to the output node, which is where the NMOS and PMOS drains meet, which is the green wire for me on the right hand side. And that should be it. Hopefully that works. So let's go back to waveforms, and we don't need the voltmeter anymore. You turn that off. Still need the power supply though, of course. So now we want to add the wave gen, and I think it said 40 to 60 millivolts peak to peak input. So I'll try the 50 millivolt option. It's actually amplitude, so we need 25 volt amplitude, millivolt amplitude, and I think it says 1 kilohertz. Let's do 1 kilohertz, run it, and let's go over to scope, and it's still running common emitter amplifier. Okay. So I gotta zoom out a bit. And maybe increase my scale or reduce my scale. All right. That looks kind of nice, I guess. Okay, so yellow is my input signal, and it looks to be about 50 millivolts peak to peak. Blue is my output signal, and it has some DC offset because, you know, the output's not sitting at 0 volts DC like the input is, but it's swinging around about 1.5 volts peak to peak. So you can get a better estimate by exporting the data, you know, obviously, but so if I go here and say this is 1.5 volts peak to peak, we can figure out the gain like so. Looks like it's about 30, just a rough estimate, and you can figure out the gain in decibels by 20 log of that number, 30. And before you move on, just make sure you get a capture of this using a snipping tool or something similar. And you're going to repeat this for 3 different values of the input signal. But the gain should remain fairly constant if you stay within this small range. It shouldn't change a whole lot. The last thing you need to do is the common mode gain, which is pretty similar, but we have some slight circuit modification we got to do. So we go back to here, and right now my input signal is just going to the left hand side, but we need it to go to both sides now. So I'm going to move my ground connections on the other side of the amplifier, which is the orange, the blue, and the black. And we're going to put these up top just so they're out of the way, because they still need to be connected together. Oops, that's not the right one. All right, and we need to connect our input signal to both gates. So let me get another yellow wire and connect that from the gate on the right to the gate on the left. Get it in there. That's not it. There we go. And I think I wired that up right. So now the same input signal is going to both sides of the input. Okay, let's try it and see if I did this right. So you'll notice my input signal is still yellow. It still looks really flat, or it still looks the same, 50 millivolts peak to peak. But my output is really flat now, and that's because this should attenuate the input signal, and the input signal is already really small, so it's just going to make it like significantly smaller. And so we need to increase the input signal, and specifically we need to do 1, 2, and 3 volts peak to peak. So let's try setting this to 500 millivolts amplitude, and we should zoom out a bit. Okay, there's the yellow signal, the input. Something else about the blue is that it's not AC coupled, so there's some offset to it. So let's see if we can fix that. I don't know if we have the ability to actually. Show coupling? No. I don't know how you. Maybe we do a high pass filter, I guess, of channel 2. Sure. Did that do it? I don't know what that actually did. That didn't help much. Filter, high pass. We want to pass the higher frequency. We want to block the lower frequency. Well, I don't know why that didn't work either. Okay, well, we really want to zoom in on it, so guess we can play with the offset until we get it to come into view. Kind of unfortunate. So you have to set this equal to the DC voltage at the output, essentially. I think that did 25 instead of 2.5. Gotta do 2.6 maybe. Alright, that got it pretty center. I had to do a minus 2.9 volt offset. And now we can increase the scale here, or decrease the scale so we can see the smaller signal. See, there it is, very tiny. and you can adjust the offset even further to really get it into view. Kind of neat. Okay, so from here we can see that the input signal is really small. It looks like maybe 20 millivolts peak to peak for a 1 volt input. It's tiny. So you want to get a picture of this to put into your document here. And we got to make some measurements here. So this is with the 1 volt peak to peak input. The output, let's say around 20 millivolts peak to peak. And you can calculate the common mode gain, which would just be 0.02, and you could convert that to decibels if you'd like. One thing to note is as we adjust this input signal to 1 volt now, let's zoom out a little bit. Okay, there's it. There it is with 1 volt peak to peak input, and the output is about 65 millivolts peak to peak. So input signal is 2 volts peak to peak, output is 60 millivolts peak to peak. So that's kind of consistent. If we adjust this to 1.5 volt amplitude, which is not default option, so we have to type that in. Okay, and we zoom this out a little bit. So input is 3 volts peak to peak now, output is, I gotta, change the scale. Alright, output is about 60 millivolts peak to peak still. That's what it looks like. But you can export the data and get a better number from that. Okay, so once you fill out this table, you can calculate the average differential gain, average common mode gain, and you can calculate CMRR using those two numbers. And that's it.